Okay, so a few remarks once the proof is completely done. So as you saw, the idea of the proof was just using the blocking method and make it formal. So you just approximate um, the sample mean using the block sums and then, block sums and the ratio and then prove things accordingly. And then you essentially finally show that the limit is the ratio of two expectations, whatever you have to prove. Now, this actually uses the full strength of dissection principle. We haven't really used the full strength of dissection principle so far in this course. We only used it in the form of use of Markov property and then conditioning, small conditioning arguments and so on. But we haven't really used it in the full strength. So this is where we are really first time using dissection principle and its full strength. In fact, you don't need, if f is non-negative, you don't need that pi f is finite. I just assumed it so that it becomes a bit easier to talk about the proof. But even if pi f is infinite, you can just go through the proof. Since f is non-negative, everything that we'll deal with is non-negative. So by using the strong law of large numbers for infinite mean, where the sample mean actually converges to the population mean which is infinite, that strong law, you can actually show that this convergence, the divergence holds almost sure. Okay, so but this is not so useful. It's more useful when pi of f is actually finite. But this is just a comment. I mean, I didn't want to complicate the proof, but the same proof can be extended. So that's used to prove it. You can check it yourself. But here f is needed to be non-negative so that you can use that version of the strong law. Now, the blocking technique is actually extremely useful. It can be modified to actually prove the central limit theorem for Markov chains. Because again, for central limit theorem, what you will have square root n here. And then again, you'll write this sum approximately as a block sum. And then you work on the central limit theorem. Of course, this will need more delicate analysis. And you will need more assumptions on the function f and so on. However, this can be shown. It's not that it cannot be shown. The broad idea of the proof is again the same blocking technique and showing that each block coming from each excursion, these are actually IID blocks. So in that sense, Markov chain is a generalization of IID, and it's not too far from IID in the sense that at least the blocks have the IID structure, at least under recurrence. So it can be proved. I'm not proving it in this course, but it can be proved. Now, following the same proof of this SLLM for Markov chains, you can actually establish other useful facts about Markov chains also. So this will be described in the next slide. So what I would do is I'll give you a bunch of exercises which will tell you the importance of this proof. You don't have to use the strong law of large numbers always, but at least the proof technique would be extremely useful. So here is the first exercise. So far we are dealing with irreducible and positive recurrent Markov chains. Now suppose you have an irreducible and null recurrent Markov chain. Now following the proof of strong law of large numbers for Markov chains, show that starting from any state I, the proportion of visits to the state K, for any state K actually, converges almost surely to 0 under each PI. Okay. So here you just have to follow the proof of strong law of large numbers, use the same blocking technique, and I have stressed where just recurrence is used, not positive recurrence. So you just follow the proof like that. You just observe exactly where the recurrence is used and not full strength of positive recurrence. And then what happens in the case of null recurrence? So you just change things accordingly and you will get this result. Once you have this result, with the help of dominated convergence theorem or bounded convergence theorem, you will get that. Instead of this, the expectation will also going to converge to 0. And therefore, this Cesaro mean is actually going to converge to 0. This is the Cesaro convergence. Now, this is extremely useful, as we will see in the next slide. Now suppose we take a Markov chain on a finite state space. Using this second part of the first exercise, using this limit to be 0, you can actually show that if Xn is actually irreducible, suppose further that say Xn is an irreducible Markov chain on a finite state space, then it has to be positive recurrent. In particular, if it's irreducible and positive recurrent, then it has unique stationary distribution. So what this says is that any irreducible finite state space Markov chain has a unique stationary distribution. Now, this will follow from the second part of this exercise, namely this Cesaro convergence of the PIKNs. The hint that I'm going to give is that recall the proof that not all states of a finite space Markov chain can be transient. Recall the proof. There, PIKNs were actually converging to 0 without even the Cesaro. It was just converging. The sequence itself was converging to 0. Here you have the Cesaro convergence. But go back to the proof of this fact and then show that not all states of an irreducible finite state space Markov chain can be null-recurrent. So in other words, if all states, okay, so it's irreducible. So if one state is null-recurrent, all states are null-recurrent. So if all states are null-recurrent, that will give you that there is a contradiction. So using the part B of this result, of this exercise here. Okay. So go back to the proof of not all states of a finite space Markov chain is transient. From there, you will be able to show that it cannot be null-recurrent, and therefore it has to be positive recurrent because it cannot be transient either. Because if one state is transient, then all states are transient. That cannot be the case. So we know that irreducible finite state space Markov chains are actually recurrent because it cannot have a transient state. So therefore, you have just to nullify that it's not null-recurrent, and that's where you'll use this exercise here to get a contradiction. Okay. Using this part, you show that even when Xn is not irreducible, no state can be recurrent, and at least one state is positive. So what this says is that for any Markov chain on a finite state space, not necessarily irreducible, one can show that no state can be null-recurrent, and at least one state has to be positive. It will follow from this first part. And finally, this part will show that for any finite state space Markov chain, doesn't have to be reducible, it has a stationary distribution. It may not be unique, but it has a stationary distribution. So these are all important facts about Markov chains with finite state space. Okay. Now, of course, when this Markov chain is further irreducible, it has unique stationary distribution. In general, the stationary distribution may not be unique, but it will at least one stationary distribution will exist. Okay. So all these are important facts about finite state space Markov chains, and this will be useful also. And I ask you to prove all these just from the technique of the proof of strong law of large numbers. Essentially, this is the key thing. Once you show this, all the other things will actually follow from it. Also, go back to the on-off process. We described it even in the last class. You start with all lights switched off, and then you choose one lamp at random and switch it on. And then again, you choose independently another lamp at random. Another time you choose independently a lamp at random and change the state of that lamp and go on. This particular Markov chain, which is essentially simple random walk on Z2 power D. So it's a finite state space Markov chain. Right? It has 2 power D many states in the state space. Since this is the finite state space Markov chain, and also it's irreducible, therefore this is positive recurrent. In particular, it has a unique stationary distribution. And we have already computed its stationary distribution with the help of reversibility. So use that to compute expected time to return to its initial state. Namely, let tau be the number of steps needed for all the lights or all the lamps to be switched off again. Okay. So compute expectation of tau. So this was essentially solved for you in the last class. The only missing piece was positive recurrence of the Markov chain, which will ensure that stationary distribution is unique. But that is guaranteed now because of the previous exercise. So now complete the proof completely and compute this expectation. So this will tell you that computation of return times is so easy once you have positive irreducibility and positive recurrence of the Markov chain. So this is where we stop today. In the next class, we'll actually start proving that first we'll show that any limiting distribution for a Markov chain is going to be stationary. And then we'll show that stationary distribution will be the limiting distribution when the Markov chain is irreducible, positive recurrent, and aperiodic as well. So aperiodicity will be important to prove that a stationary distribution is actually, the unique stationary distribution is actually the limiting distribution of the Markov chain. Of course, we may not be able to complete this proof in the next class, but at least we'll start towards the proof. Okay, so let us stop here today.